In this video, I'm going to talk about a linear application of the operation amplifier, which is rectification. I will introduce rectifiers in the several applications of nonlinear applications of the operation amplifier, and then I will focus on a specific circuit to rectify a signal. Well, the implementation of a nonlinear function of the operation amplifier, which is the rectifier, needs to have an operation amplifier with negative feedback, but including in the circuit nonlinear elements such as diodes or transistors. Okay, this is the case of the rectifier, and an example of circuit of rectification would be the following one. Here we have negative feedback and we have two nonlinear components, which are the two diodes present in the circuit. Let's analyze this circuit and let's demonstrate that the output voltage is the input voltage rectified. So to analyze this circuit, I'm going to suppose a first case in which the input voltage is positive. Okay? If we suppose that the input voltage VE is positive, let's take a supposition for the state of the diodes. And I'm supposing that diode 1 and diode 2 are off. This would be my first supposition, which I have to demonstrate it's true or false. So with these two diodes off, the circuit I have left would be the following one. Here I would have R1, the input, then the operation amplifier with negative feedback. Here I would have R2 connected to the output Vs, and the two diodes are off. So this is the circuit remaining. Now let's check whether it's true if these diodes are off. So if here I have a voltage which is positive, VE, and no current circulates through R1 and R2 because this is open circuit, I can say that here I still have VE. And because there's no feedback at all in this circuit, I can say that because V minus, which is VE, which is positive, is bigger than V plus, which is 0, okay, this is VE, which is positive, is bigger than 0, then the output of the operation amplifier will be minus saturation voltage. So here I have a negative voltage and here I have in VE a positive voltage, and because no current is flowing through R2, in Vs I will just have VE, a positive voltage. That makes that my diode 2 is on, because this is positive and this is negative. So this should be on, and if this is an ideal diode, I could suppose this is a short circuit. However, the voltage I have here in this diode, diode 1, because here I have minus saturation voltage, and in the cathode I have a positive voltage, I am sure that this diode is off. So this was true, diode 1 was off, but diode 2 is on. And this is the real circuit I have whenever VE is positive. So in this case, if I analyze the new circuit with negative feedback, in this case, I don't have here anymore minus saturation voltage, and I don't have here anymore VE. What I actually have is a usual circuit, an inverter amplifier, in which I have negative feedback, and I'm going to analyze this circuit as it is now, and I can say that the output voltage Vs is going to be minus R2 over R1 times VE. So this is what I get when the voltage VE is positive. What happens now if the voltage VE is negative? I'm going to start with the same supposition as before, and I'm going to say that diode 1 is off and diode 2 is also off. So the circuit I have would be the same as before, with no feedback at all. Here I have R2 and here the output, R2 and R1. And here I have a negative voltage VE. What happens when I have this negative voltage here? Because no current flows, here I have also the negative voltage VE. And now I can say that V plus is bigger than V minus, because V plus is 0 and V minus is a negative voltage. So that makes that at the output of the operation amplifier, I'm going to have plus saturation voltage. And in Vs, because no current flows, I have VE, which is negative. So what is the real state of my diodes? Let's check. Here I have in the anode of diode 2, I have a negative voltage, and in the cathode a positive voltage. So this is really off. This diode is off. But what happens with diode 1? In the anode I have a positive voltage, and in the cathode I have a negative voltage. So this diode is not on. It's not off, but it is on, and because it's an ideal diode, I'm going to consider this is a short circuit. So my first supposition was false. Diode 1 was on and diode 2 was off. This is the real circuit I have, and now if I analyze this circuit with the real values of the voltages, I'm going to say that here I have negative feedback, so V plus is equal to V minus is equal to 0. And because no current flows here, in Vs I have the same voltage as in V minus, which is 0. So I can say that when VE is negative, the output of this circuit is going to be 0. So when VE is positive, I have that the output is going to be minus R2 over R1 times the input. And when VE is negative, Vs is going to be 0. Let's demonstrate that this is a rectifier, because if I introduce a sinusoidal wave, VE, when VE is positive, the output will be amplified and negative, and when VE is negative, the output will be 0. So this is what we call a half-wave rectifier. The wave has been rectified. Now, how can we build a double wave rectifier if we want to rectify both of the waves? This would be the circuit we can build to obtain a double wave rectifier. So this is the first circuit we have analyzed, and here we have a summing block. Let's analyze it and demonstrate that this is a double wave rectifier. So from the previous analysis, we have obtained that when VE is positive, Vs was minus R2 over R1 times VE. In this case, both resistors are the same, so this is going to be minus R1 over R1 times VE, which is minus VE. And when VE is negative, we know that Vs is 0. Now let's analyze the second part of the circuit, which is a summing block. In this summing block, this is an inverter summing block, and I know that the output is going to be minus the feedback resistor, R2, times one of the inputs, Vs over R2 over 2, plus the other input, which is VE over R2. What happens when VE is positive? When VE is positive, VO is going to be minus R2 times the value of Vs for VE positive, which is minus VE over R2 over 2, plus VE over 2 over R2. If we simplify this, we will obtain that VO is going to be equal to VE. Simplifying this equation. And what happens when VE is negative? When VE is negative, VO is going to be minus R2 times Vs, which is 0, plus VE over R2. That means that in this case, VO is going to be equal to minus VE. So if we represent the input as a sinusoidal wave, which is VE versus time, when we calculate the output, this will be for VE positive, VO is going to be equal to VE, and for VE negative, VO is going to be the inverse of VE, then positive again, then negative. So here we have a double wave rectifier. In conclusion, we can build a rectifier, a half-wave rectifier or a double-wave rectifier using an operation amplifier with negative feedback, but including nonlinear components such as diodes.